Hi, in this video, we want to take a look at a case study that is looking at the effects of critics for wine prices. Okay, so this is an example taken from A Modern Approach to Regression with R. Here is the textbook's website. All right, so what we want to do, we want to look at the variables that contribute to the price of a wine at auction, and how, like specifically, how much do the critics influence the price. Okay, so first thing we're going to do, load the data. All right, and so here's my data set. Now, something I did was I saw that I have a column of wine names, and the names are unique. So each name appears only in one row. All right, well, it would make sense to go ahead and put the row names as the wine. That way, when I look at my diagnostic plots, it'll be easier to see what's going on. I don't have much knowledge about wines, but someone who does might be able to look and go, hey, that makes perfect sense, or hey, that is wrong, when they have subject matter knowledge. Now, something else I like to do, I like to order my data so that it's set up so that when I look at it, when I see like the extreme values, it will be easier to interpret things in terms of like the row. If I look at the top row, I want like the lower target values, the bottom row, the greater target values. And this helps with some of the diagnostic plots. You'll notice that I order everything by the far right column, then I move over to the left on the variables that are used in the regression model. So by doing this, I'm kind of saying like the most important, like just naively, not knowing what's going on. I haven't really worked with this yet, but I'm sorting things by the far right being the least important for sorting, the far left being the most important. The far left of the variables is going to be the target variable, the actual price. Now, column 1 is the wine's name, so you'll notice that I don't include 1 in there. Okay, so now I always like to have colors correspond to my target variable. That helps things pop out so I can see what's going on. So I go ahead and take the target variable. I don't need a sort on this one, but I did anyway, absentmindedly. I go ahead and for each unique value of the target variable, I define a color, and then I just attach onto my data frame the colors like that. And to do this, I go ahead and I take the vector of colors and I say that the names correspond to the prices. Now, something about this, names are always character values, so therefore I have to have as character when I put the target variable onto there. Otherwise, it's going to take an integer and look for an index. That's going to be a problem. Okay, so now let's actually build our initial model. So we're going to take the log of the price, and we're going to say that depends on cold wine, first growth, log of Parker points, critic, Pomerol, vintage superstar, log Coates points, another critic, and then 95% or percentile and above. Okay, so one thing I did before I made this video, I actually built the model and I put my variables in order by the p-value, most statistically significant to least statistically significant from the summary command. Why do I do this? I like to have my variables sorted so that as I work through, I kind of have like a feel for what's most important, what's least important, and as I go through, all right, at this point, I'm just gonna get rid of everything. It is usually what I do in real life when I have a lot of variables. I just start working through down the list until I get to a certain point where, all right, I don't think these are going to help if I need to do variable reduction. All right, so now I've got my model. I'm going to go ahead and append the fitted values and the residuals onto the data frame. That way, as I make my plots, I don't have to redefine these. So I'm taking the fitted values, and so these are the fitted values on the observed data. And I'm taking standardized residuals. Now, something to always remember, whenever I'm working with standardized residuals, I'll always get standard deviation of 1 and mean of 0. So anytime I'm doing multiple linear regression or simple linear regression, every single time the residuals will add up to 0. So the mean is always 0. That's not a problem. But if I have a really, really sharp, really, really tight, well-fitting model, and I do standardization, it's going to rescale it so that I have standard deviation 1 regardless. So standardized residuals may not be the way to go if I have a really tight, well-fitting model. I'll have to be mindful of that as I go forward. Ends up not being a problem here, but I have to be ready for that. All right, so let's start looking at some diagnostic plots. So first thing we're going to do, we're going to go ahead and plot the fitted values by the observed target variable values. All right, so if I have a good model, the dots will be really close to the line x equals y. Okay, let's see what we get. I look through and they're not too far off from each other, but it could be better. Now, why is it that we're doing fitted values and observed target variable values? Well, remember, we're doing multiple linear regression. We have multiple predictor variables. What I'm doing, I'm basically summarizing the entire model with these data points and then doing a scatter plot with the observed target variable. All right, could be better, could be worse. Okay, so now let's go ahead and let's look at our residuals by our fitted values. Remember, if I see a pattern, there's a problem. And remember, as I look at the color, the fitted values should correspond to the true observed values of the target variable. So it's okay for the colors to shift like this. That's fine. All right, now let's go ahead and look at our residuals by our observed target variable. All right, I don't really see a pattern. I see a little bit of scattering out. I also want to look at vertically, how is the variance vertically as I move from left to right of the residuals? Do I see like a horn shape, or do I see some other kind of weird shape in it? If I do, then I need to start doing something to worry about that, because if I want to do hypothesis testing, I need to have constant variance of my residuals. All right, now let's go ahead and start doing the same scatter plots with residuals, but this time along the x-axis, I'm using my predictor variables. So I'm looking for a pattern and in the dots, and I'm looking to see, do I have constant variance of dots as I move from left to right? If I don't, I need to make some adjustments. Now remember, wherever I have like more values, it's gonna just look more spread out by the dots. So it's more of an impression than like a measurement on this. There are ways to actually measure it, but when we have like a continuum of values or nearly a continuum, it gets kind of like, you have to decide on cutoffs, and it's kind of difficult at times. Okay, so let's look at the box plot where Colt wine is the predictor. All right, so we see relatively constant variance. That's all right. So whenever I see the lines lining up, if I see the median, if the boxes look like this, the lines are like cutting into each other's box. So you see the median line is within the range of the other interquartile range. If the line here is within the interquartile range of the other, they're usually pretty close to each other. So this is not really screaming to me that Colt wine is going to be that important. And I really see the same thing for first growth. Now, the larger the data set, the more of the more statistically significant a shift will be. So this is a relatively small data set, so I'm not seeing a whole lot of difference here. The skewness could be from values that aren't like having very few ones or very few ones in the data set. Now here, Vintage Superstar is very rare, and I don't think that this is a huge issue to worry about. I'm following the example from the textbook, and the author ultimately keeps this in there. And I can honestly go either way on keeping it or getting rid of it. You know, whenever I see whenever I have a dummy variable with very few ones or very few zeros, I usually like to get rid of it. Just my preference. And then now we have a percentile 95 or above. And, you know, we see relatively similar spread on the interquartile range. I see that the medians are pretty close to each other. So I'm not seeing a big difference. Okay, so now let's go ahead and look at the plots that come from the linear model. All right, the QQ plot shows that the residuals are not normally distributed. I went ahead and I looked at the histogram, and honestly, it's close enough for what we're doing. It just has to kind of look like a bell curve. It just has to be like not extremely far away. It'll be good enough for what we're doing. Now, if we take a look at the Cook's distance, what we're going to notice is that since I sorted the data beforehand, we're going to see that the ones that have largest Cook's distance are also the values that, or the observations that have the extreme observations. So here's the residuals versus fit. Don't see a pattern. I want to, if I see the line is doing something besides being relatively horizontal, I worry. All right, so I conclude that this is not normally distributed, but it's close enough to a bell curve to proceed. I don't see a pattern. And remember, 3 points are always getting labeled, so don't panic when I see 3 points every single time. Something that's jumping out at me is I keep on seeing the same lines over and over and over. So I see Le Pen here. Got this wine. Got the same three. Same three. This one is different, but I see Le Pen again. Le Pen. Now, because I sorted the data, it's easier to see that the extreme values of our target variable correspond to some of the largest Cook's distance. That's something to be, you know, to note, to be aware of. There might be a good reason for that. It might be that the model doesn't really fit that well on the extreme ends. That's something that I might want to consider. This small of a data set, I probably would not start digging into a more advanced model. I'd probably just leave it as is and just kind of keep that in the back of my mind. If I ended up having, like down the road, like a much larger data set and working on the same project, then I might go, you know what, maybe a linear regression isn't the best way to go. But for the size of the data, I'm satisfied with this. All right, now we're taking a look at leverage and standardized residuals. This one is popping up again. So I'm starting to feel like this one, if I had, if this was like real data, I would want to contact the people who were involved, see if there's something special about this. Was there something else going on that makes it different? Should I throw this out from the model? Is something I would definitely be considering at this point. Here it is again. All right, so now let's go ahead and look at the summary of the full model. And something that jumps out at me is that the 95% and above is not statistically significant. And I've got plenty of variables going on. Honestly, my experience in real life modeling, usually having one predictor variable that's not statistically significant is okay. I personally will start doing, I will remove variables until I only have one that is not statistically significant. That's just how I usually roll with it. One thing you always want to look for overfitting is if you see a difference between the adjusted R squared and the regular R squared. If they start deviating from each other, you have a problem. Definitely statistically significant. You know, honestly, if this is real world data, a 0.92, you know, R squared, adjusted R squared is phenomenal. All right, so let's go ahead and take a look at the variance inflation factor. All right, so remember, this comes from basically regressing a predictor onto the other predictor variables. Okay, and so if I see that we have a strong correlation between one variable and the model that predicts that variable with all of the others, if that ends up giving me like a big value, then I probably have a problem with my data, that the variables are redundant in their information. If they're redundant in the information, then I need to get rid of one. Variance inflation factor is a good way of measuring, do I have information redundancy in my predictor variables? All right, so something that jumps out at me is that the log of Parker points is much bigger than the rest. All right, so, but honestly, this isn't a hugely concerning variance inflation factor. Around 5, we start worrying. 10, you need to do something about it. All right, so let's look at the marginal model plots. So here we're looking at the fitted values. And if I see that the non-parametric line and the modeled line fit tightly, then things are pretty good. So whenever I see the red and blue are tight, I'm happy. Okay. Let's roll along. All right, a little bit to the left and right, we see some deviation. Kind of want to be mindful of that going forward, but I'm still accepting it. Now add variable plots. All right, so here, what this is asking, this is giving me, or not, this is giving me visual information on, does this one variable add to the other predictors? This is, you know, if I have all the other predictors going on, and I throw this into the pot, does this provide informative value? All right, so now, this is one of the reasons why I like to order my predictor variables in from what looks like it's going to be the most important to least important, because here I can see kind of a trend as I move down the list. If I see a flat horizontal line, then I'm going to consider getting rid of that variable because the other predictors are accounting for the information that's in there. So here I see a decent slope. So, all right, that's good. Let's keep that one going. I see a decent slope for first growth. Keep going. Parker points still has a good slope. All right, here still have something of a slope going on. Same thing for vintage superstar. Now here you can see that there's very few points, and with this few of points, I would honestly consider throwing this one out just because I have so few non-zero entries. I mean, if I only have 2 here out of the entire data set, I mean, I'm basically banking on these 2 data points a lot. And if I'm banking on these 2 data points a lot, then I really am taking a risk on using this in my model. It might just be that I've got 2 outliers floating around that happen to correspond to these 2 rows. And in that case, I'm vulnerable to having a bad model. I would get rid of vintage superstar at this point. All right, now here we have the other critics points, and you can kind of see that the lines are getting kind of flat, more horizontal as we go down. Now here, that is definitely flat. Okay, so here, what this is telling me is that the 95th percentile and above data is not informative or does not add to the other predictors. The other predictors are already capturing the informative value of this vector for all practical purposes. So this means that this vector is redundant when I have the other ones present. Now, which ones are the ones that are making it so that it's redundant? I don't know. I don't care. I'm just throwing it out and I'm going on with my life. All right, so I'm going to reduce the model. I'm going to get rid of the 95th percentile and above. And basically, I just build the model like I did. And you'll notice I didn't lose anything. I mean, everything's good. Now, the numbers kind of shift a little bit, but I think the adjusted R-square is just a touch better. But, it's pretty much the same. Getting rid of that one vector did not, reduce the value of my model. I'm going to go ahead and run ANOVA just to see if this type of sum of squares is looking good. Everything's looking good. Everything's statistically significant. And now I'm going to run ANOVA comparing the reduced model to the full model. If I see statistical significance, that means that the full model has more informative value than the reduced model. If I fail to reject the null hypothesis, then I conclude that the two models are equally informative. If they're equally informative, then I want to go with the reduced model because it's simpler. All right, so here we see that it's not statistically significant. Not statistically significant means that we have equality. Remember, the null hypothesis always has an equal sign. All right, so how do we word this with an equal sign? The two models are equally informative. Since they are equally informative, I'm going to go with the simpler of the two. That is the reduced model. Boom, we got this. All right, that's all I got for you. Take care and goodbye.